So when heat is transferred from one object to another, are losing and gaining. So when heat is transferred from one object to another, the objects are losing and gaining what we call thermal energy. Heat is thermal energy in transfer, in motion from one place to another. So heat is the thing that transfers. When a substance gains heat, its thermal energy increases. Sometimes thermal energy is called internal energy. And so in the special case here, when there's no phase change, and by phase change I mean like solid to liquid or liquid to gas, when there's no phase change, this transfer results in a temperature change. And so what we'll say is Q is proportional to the change in temperature, where this is the heat, and again this is the heat that gets transferred, and this is the temperature change. We usually write this proportionality as an equality with two constants. We say Q is equal to m times c times delta T, where this is the mass, and this quantity C is called the specific heat capacity, sometimes just called the specific heat. So if you heat an object, add heat to an object, the temperature change you get depends on how much mass is there. That should sort of stand to reason, right? If you put a fixed amount of heat in, the more massive the object is, the smaller the temperature change is going to be. The less massive the object is, the greater the temperature change is going to be for a specific heat, for a certain quantity of heat. It's also true that how the temperature changes depends on this quantity, the heat capacity, which is sort of carries some information about the chemistry of the item that's being heated. Metals, it turns out, have small heat capacities, and so compared to a non-metal, it'll take a smaller amount of heat to get the same temperature change than it will for a non-metal. If this number is really big, it takes a small number here to get a big number here. And so we'll talk about some examples. This does not apply when there is a phase change, and so we have to use a different equation. But in a lot of cases, you don't come across a phase change. The melting point and the freezing point of the melting / freezing versus the boiling / condensation points are often pretty far apart, and so you can have a lot of stuff that happens between those that just uses this equation. So we're going to just list a few specific heat capacities. That's the C in this equation. And notice, since heat is a unit of energy, then the unit for specific heat capacity, I'd have to divide out the mass and the temperature, and so it would be joules per kilogram Kelvin, and that's what you see here. It's joules per mass times temperature, right? Notice it doesn't. These two are the same. It doesn't matter if it's degrees Celsius or degree Kelvin because it's a change in temperature, and since changes in temperature and Kelvin are the same, the only thing that's different is the absolute value. The difference between temperature of boiling water and temperature of freezing water in Kelvin is 100 and in Celsius it's 100. Any temperature difference is going to be the same. So sometimes you need this if you're using degrees Celsius in your problem, or you might need this, but they're interchangeable as long as you're looking at temperature differences. So I was just going to write down a few of these. So aluminum is 900. Maybe I should put a little line here. Glass is 840. Ice is 2100. Iron or steel is 452. We'll probably be rounding that. I've seen slightly different numbers for some of these. This is 128. That's lead. And water is it's 4186. I might use 4180 for that. I can't remember. You'll see different numbers for this based on how it's calculated because it's kind of temperature dependent. Notice it says 15 degrees C. Sometimes they'll do it for liquid water at 0. Sometimes they'll do it liquid water at 20. Sometimes they take an average of them. And so sometimes you'll see 4180 or 4184 or 4186. That's a small difference, so it hardly matters. It's way under 1% difference. So these are typical numbers that we would use in a problem, say, and if we have other numbers, we'll just give them to you in the problem. You can look them up in your textbook. So a 0.5 kilogram aluminum pan with 0.25 liters of water is heated from 20 degrees C to 80 degrees C. What's the heat required, right? So we have to transfer, we could say Q for the water is equal to M water times C for the water times delta T for the water, right? And then we could say Q pan is equal to M pan, C pan, delta T pan, right? And then we can say, well, delta T water equals delta T pan, right? They both do the same thing from 80 degrees from 20 degrees to 80 degrees, so it's 60 degrees Celsius, right? It's 80 minus 20, right? And so M for water is 0.25 liters times 1 kilogram per liter, which is 0.25 kilograms. You could do a more sophisticated transfer by first converting that to cubic meters. That's 1,000th of a cubic meter, and then multiplying it by the density of water, which is 1,000 kilograms per cubic meter, and you get back to 0.25 kilograms that way. And so we can say Q water is equal to the mass of water, which is 0.25 kilograms, times the specific heat capacity of water, which is 4186 joules per kilogram Kelvin, say, or per kilogram, I guess, degrees C for this problem. Doesn't matter. Times 60 degrees C, which is 62.8 kilojoules. Right. Q for the pan is equal to the mass of the pan, which is 0.5 kilograms, times 900 joules per kilogram degrees C, times the same 60 degrees C, right? And that's 27,000 roughly 27 kilojoules. Right, and so then I could say, so Q total, the total heat transferred, is equal to Q water plus Q pan, which is approximately 80 kilojoules. I could ask question B here. What fraction of the 80 kilojoules is used by the water, right? It's just the fraction is 62.8 kilojoules over 80 kilojoules. Which is about 78%. And so notice that even though there's more mass in the pan than there is mass in the water, right? This was twice as much mass in the pan. The fact that the heat capacity of water is over 4,000 and the heat capacity of aluminum is only 900 meant that the water actually used a lot more. A much greater fraction of the heat that was sent into the system ended up heating the smaller amount of water, because of the heat capacity of the water. So this is a calorimetry problem. A 0.5 kilogram lump of aluminum at 150 degrees Celsius is placed in a 0.25 kilograms of water at 20 degrees C with in an insulating container. So it looks like this. Here's my container, right? Here's my water, and then I have a little piece of aluminum in there. That weighs half a kilogram, right? Aluminum is denser than water, so it can be a little more massive, even though it's smaller in size. And so what we know is that since the system is isolated, Q aluminum plus Q water is equal to 0. That is to say, the heat gained by the water is lost by the aluminum. And so M aluminum, C aluminum, delta T aluminum is equal to plus M water, C water, delta T water is equal to 0. And so let's just identify some of these things. Mass of the aluminum is equal to 0.5 kilograms. Mass of the water is equal to 0.25 kilograms. Right? C for aluminum, we've already said is 900 joules per kilogram Kelvin. C for water is 4186 joules per kilogram Kelvin, right? T initial for the water is 20 degrees C. I'll call that T water initial. And then T aluminum initial is 150 degrees C. And so so we know a whole bunch of things here. What we don't know is what the final temperature, but we know that T final is equal to T final for aluminum, or T aluminum final, or T water final, right? If the system sits long enough, it reaches equilibrium, and that's what they're asking us for. You put these two things together, what's their equilibrium temperature, right? And so if I sort of expand this out, the thing we're looking for is T final, and so I can write, well, this becomes the mass of the aluminum times C for the aluminum times T aluminum final minus T aluminum initial, plus mass of water, C water, times T water final minus T water initial equals 0. And the thing that we want, first we recognize that these two are the same, and so I get mass of the aluminum, C for the aluminum, times T final minus T aluminum initial. Right? T final doesn't have to specify the aluminum because the final water temperature and the final aluminum temperature are the same, plus mass of the water, C for the water, T final minus T water initial is equal to 0. What we're after is T final. We've already said, based on this list over here, we have this number and 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 this number. The only number we don't have is this one. And so I'm going to have to do a little fancy algebra. I'm gonna distribute this thing through these parentheses, and so I'm going to get mass of the aluminum times the specific heat capacity of the aluminum times T final plus mass of the aluminum, C for the aluminum, times, it's going to be a minus T aluminum initial. In other words, this times that minus this times that, right, plus mass of the water, C for water, T final, minus mass of the water, C for the water, T water initial equals 0. Well, I've done expand this. Now I've got these guys. I want my T final, right? And so I'm going to do a little fancy work. I'm going to move these the two negative ones over to the other side of the equal sign. And so this is going to give me mass of the aluminum, specific heat capacity aluminum, T final, plus mass of the water, C for the water, T final, equals mass of the aluminum, C for the aluminum, T aluminum initial, plus mass of the water, C for the water, T water initial. I'm going to have to race and go back up to the top, but what I'm going to do is I'm just going to factor this thing out. Maybe I can get one more line in there. Can I get one more line in there? Maybe. So I'm going to factor the T final out of here. And so I'm going to say, look, this is mass of the aluminum, C for the aluminum, plus mass of the water, C for the water, times T final. I just factor the T final out of these two guys. Plus, and I'm going to leave the equals, and I'm going to leave this side the same. Mass of the aluminum, C for the aluminum, T aluminum initial, plus mass of the water, C for the water, T water initial. You could plug numbers in here, but I think it's better not to, at least initially, while we're at this stage, because it's easy to make a mistake cranking through, and a lot of your problems are going to look almost the same, and so it's nice to just practice with the algebra. So I'm going to erase some lines up here, right? And now I'm going to say T final. I'm going to divide both sides by the thing in parentheses is equal to mass of the aluminum, C for the aluminum, T aluminum initial, plus mass of the water, C for the water, T water initial, over this whole thing in parentheses. I just divide by both sides by the whole thing in parentheses. So it's mass of the aluminum, C for the aluminum, plus mass for the water, C for the water. And if you notice on the right side of that, I have all the numbers I need, right? And so I can, I'll back up here because I'm going to have to start sticking numbers in. The thing about sticking numbers in is you've got a whole bunch more characters to write, right? That's why it's another reason why it's so much better to keep letters until you absolutely need the numbers. So the mass of the aluminum is 0.5 kilograms. C for the aluminum is 900 joules per kilogram degrees C, times T aluminum initial, which is 150 degrees C, plus the mass of the water, which is 0.25 kilograms, times C for the water, which is 4186 joules per kilogram Kelvin, or per kilogram degree Celsius. Again, it doesn't matter. I keep saying that for these things, times 20 degrees Celsius, all divided by the mass of the aluminum, which is 0.5 kilograms, times times C for the aluminum, which is 900 joules per kilogram degree C, plus the mass of the water is 0.25 kilograms, times 4186 joules per kilogram degree C. And when I calculate all that out, I get, and so we should have some idea of what this number is going to be. You should have some sense of whether the number is going to be closer to the 20 or closer to 150. First of all, I think we can all agree, hopefully, that it's between 20 and 150. So if you're taking the multiple choice test, you can rule out the numbers that aren't there, right? We already did an example where we had a 0.5 kilograms of aluminum and 0.25 kilograms of water, and we found that it was harder to raise the temperature of this piece than this piece. And so the number, whatever it is going to be closer to this guy, and it's going to be, I think, about, what were the numbers? I can't remember the numbers we got in the last problem, but maybe if you look at the difference between those 130, maybe a quarter of that, so maybe 150, 160, 50 or 60 degrees Celsius, something like that. And so when I evaluate this, if I crank through all this thing, I get 59.1 degrees C. And so this number makes sense to me. It's between these two, and it's a good bit closer to the water, which has the much higher heat capacity, which more than enough compensates for its smaller mass. It's pretty dense, but you can do all that. So when we were talking earlier about the specific heat capacity and things like that, we started that conversation by saying, as long as there isn't a phase change taking place, in other words, as long as you're not going from liquid to gas or from solid to liquid, then Q equals MC delta T works. However, it doesn't work in phase changes. And so we're going to handle those here. So consider a compound at its phase change temperature. Or more than one phase change temperature, right? It could, it could be water at either the freezing point or the boiling point, freezing, melting, or boiling condensation. So, for example, water at 0 degrees C or 100 degrees C. So, for example, here is a cup of ice water. All of the water in the cup, as long as it is mixing reasonably well, you might have to gently stir it or something like that, as long as you're not allowing the temperature to get redistributed somehow. As the heat is added, the temperature will remain constant in the case of ice water at 0 degrees Celsius until all of the compound has changed phase. In other words, if the cup of water is insulated, it'll stay at 0 degrees C until all the ice melts, and then it'll raise up. And the reason is because ice melts at 0 degrees C. And so if some other water were to raise its temperature, so if some of the liquid water in the cup were to get its temperature above 0 degrees C, the heat from that would just be absorbed by the ice, and that water would go back to 0 degrees C as more ice continued to melt. And so materials stay at their phase change temperature until all of the compound has changed phase. And so the equation for this looks like Q equals ml, and there's a specific one for the freezing melting transition, and for the boiling / condensation temperature transition. And so I'll just start out with the freezing melting. So at the melting freezing temperature, so you have water at 0 degrees Celsius. If you pull heat out of it, the water will freeze. If you add heat to it and it's ice, the water will melt. And so the ice will melt. And so depending on whether you're adding heat or removing heat, so the equation for this is Q equals m L sub F. So m is equal to the mass, and L sub F is called the latent heat of fusion. Notice it doesn't have the temperature in here. There's no temperature change going on like there was in Q equals mc delta T. This just says the heat required to melt ice is the mass of the ice times the latent heat of fusion of ice. And so again, here is the m equal mass, and L sub V is called the latent heat of vaporization. And so for water, L sub F is equal to 334,000 joules per kilogram. Notice, if this is joules and this is kilogram, it's got to be in joules per kilogram. And the latent heat of vaporization is L sub V is 2,260,000 joules per kilogram. So it takes a lot more energy to take water from the liquid to the gas phase per kilogram than it does from the solid to the liquid phase. It's easier to melt water than to boil water. So 3 ice cubes at 0 degrees C and each of mass 10 grams are put in soda. The temperature of the soda is 20 degrees C and the mass of the soda is 250 kilograms. It should be 250 grams. Caught that. If I wanted to, I could say equals 0.25 kilograms. would be better, right? And this top one is equal to 0.010 kilograms. Are put in soda. Okay, what is the final temperature, assuming the system is insulated, and the specific heat capacity of soda equals the specific heat capacity of water, right? And so we can say, look, Q soda plus Q ice is equal to 0, right? When I put the two together, however much is gained by the ice is lost by the soda, however much is lost by the soda is gained by the ice, right? And so we have a couple of things going on. Let's just start with the ice. Q ice is equal to mass of the ice times the latent heat of fusion of the ice, right? Because the amount of heat absorbed by the ice is going to be the amount required to melt the ice, right? Plus mass of the ice, C for water, because after it's melted, now the water that the ice melted into warms up, right? And then delta T for the ice, right? Similarly, Q soda is equal to the mass of the soda times C for water, because that's what we said, times delta T for the soda, right? We're going to agree that T final is equal to T final for the ice. I know at this point the ice is water, but we're just going to call it the ice, minus, or I should say T, this is going to be a little confusing, ice final minus T soda final.